Hello and welcome to lecture number 15. In the last class we looked at the potential field method in 2D, and then we saw how to use the potential field method in 3D applications, and then we looked at navigation functions also. So today we'll move on to the next topic, which is basic search. That means whatever we have done till now, like we have used things like visibility graph, then probabilistic roadmap methods, okay, in which we found a network of paths. But now when you have found a network of paths, you need to find out which is the best path. Now, how do you know which is the best path? Now, what do you mean by the best path? Probably is the shortest path. Okay, so today we'll look at basic search algorithms, and then we'll move on from here. Okay, so today we'll be looking at basic search, and then we'll look at trajectory planning. Now, what we have been doing so far is we looked at various methods like roadmap methods, in which we had a visibility graph method, in which we found a network of paths to take you from an initial point to a final point. Then we looked at probabilistic roadmap methods. Then we looked at RRT. Okay, now in all of these methods, for example, just very quick revision of what we had done is in visibility graph method, what we had done is we have a number of obstacles, and what we do is we connect these obstacles by straight lines. Okay, so these are obstacles. This is my start point, and that's my goal point, just for example. Okay, and what we do is we basically connect each of these vertices by straight lines, right? That is what we call the visibility graph method. So basically what we are doing is we are getting a number of pathways. We are trying to generate pathways that will take it from the initial point to the goal point. Now this is approximately what we have been doing. Now what we see is that there can be more than one path. Okay, so for example, in this case we have one path which can go like this. Sorry, there are more paths actually. There can be large number of paths. There is one path this way also. Okay, so what we see is that there can be one path that will go like this, that is going to go from here like this, like this, like this, and like that. There can be another path which can go from let's say from this side, like this, like this, like this. So these are all paths, right? Now if there are so many paths, then we need to choose which is a good path or which path should we follow. Okay, so as you can see that there are a number of paths, a very large number of paths, and now the question comes, which one will you follow? Similarly, if you look at probabilistic roadmap, so in probabilistic roadmap methods, okay, what we do is, again, we have let's say a workspace like this, in which we have a number of obstacles. So there is one obstacle here, there's one obstacle here, and my start point is here and my goal point is there, for example. And what we do is we generate a number of paths. So these are the various nodes. So basically we generate nodes which are possible, and then we connect nodes by edges and see whether I can connect it from the goal point to the. So these are nodes, and two of the nodes are connected by edges. Okay, but in all these cases what we see is that we are making a network of paths. Okay, then the question comes, which path am I going to take? Another example was we looked at RRT, rapidly expanding random trees. Okay, in which case we had, let me draw it here, just a very quick revision, where we had maybe an obstacle here like this, and this was my start point, that's my goal point. Okay, so this is start and that is goal. What we do is we grow a tree from here. So we grow a tree like this, and these are branches which are going out. Okay, so these are various branches of the tree which are going out, and then we try and see whether we can connect the node. We can connect so these are different branches which are going out, and then we try and see whether we can connect the goal point to the start point by following some path. Again, here you see that there are a lot of paths. So the question comes that how do you search for a path? Now two terms that we are using here. Number one is a node. Okay, so each of this is a node. That means the robot, it is possible for the robot to be at that point. Okay, so we can call a node. In this case, we are calling vertices. Okay, so that's a vertex. So the node and a vertex essentially mean the same thing here. And then nodes are connected by what we call paths, pathways or edges. So let's call them edges. So nodes and edges. So nodes and edges makes network of paths. Okay, so we have node and we have edges. And this collection of nodes and edges are make up what we call the a network of paths or pathways. There are several algorithms which are there. We'll look at some basic search algorithms. Now the search algorithms basically means what is it searching for? It is searching for a path. Okay. Now it can be a best path. For example, it can be the shortest path, or it can have other constraints. For example, time can be a constraint, dynamic cost can be a constraint, okay, energy can be a constraint. Okay, so it depends on what do you mean by an optimal path. What is it that you're looking for? As I come along, I'll be explaining what these mean. Okay, so the first algorithm, the easiest is or the earliest is in somewhere in 1959 by Dexter. So Dexter was a computer scientist, and he was basically looking at the shortest path when there is a network of paths. Now a modified algorithm of that, or a more advanced one, is A star search, and then from A star search we have what is D star search, or dynamic A star. So this is my dynamic A star, okay, so which is called D star. So we'll look at very basic search algorithms today, and then we'll move on to look at trajectory planning. Now what we are basically looking at is a network of paths or graphs. Okay, in our case it's a roadmap. Basically it's a network of roads. Now there can be different kinds of types of graphs. For example, you can have a tree type, in which case you have a root. So this is my root, and from the root you are having branches, right? So the branches are going out like this. Each of this is a node, and this is an edge, and that is a node. Now you can also have a graph which is like this. For example, a collection of edges and nodes which are not tree type, but a graph where you're having nodes like this, and these are edges. Okay, so these are two types of networks that you can have, or graphs. Now we can divide this search in two types. One is an uninformed search. Okay, this uninformed search uses no information obtained from the environment. Okay, and it is some kind of a blind search. Say for example, when we talked about wavefront wavefront planners, they were basically blind searches. So it basically means something like this. This is a wavefront search. So we have an obstacle. Okay, we number this as 1 1 1 1 1. The next is 2 2 2. Okay, so this is basically a grid search. So we make grids like that, and what we do in this wavefront search is that if there's an obstacle here, we name that as 1, okay, that grid. The next grid will become 2 2 2. Then the next grid will become 3, in that way. So basically in this case the search is propagating. It's like a wavefront. That's where the name comes from, and it's a blind search. It doesn't know what other obstacles are on the way. Where is the goal? Where is the start point? It simply searches like a wave which is expanding from one point and going in all directions. So that is uninformed search. So the other kind of search is what we call informed search, where we can basically evaluate a function. A function, the function could be evaluating the path length. Okay. Suppose I want the shortest length path. Then I'm going to evaluate a function which will take the sum of all the edges and say that, okay, if you go this way, it is fastest. Obviously, these are more faster. They are more efficient. So informed search is going to be faster than uninformed search. Now, when we are talking about a distance, okay, let's take this example, which we are all familiar with. For example, we are trying to go from a point. This is Google Map, for example, which I'm sure all of you have seen. Now I want to go from this point to this point. Okay, so this is my start point, and this is my goal point on a Google Map. Now, it may appear that a path length will be shortest if it's a straight line. Path length, okay, from the start point to the goal point is a straight line like this. Okay, but on this Google Map, which is very clear that you can go only on where a path exists, or on the roads, right? You can't fly across like that. So the road is like this, like this, like this, like this, like this, like this, like this. Wherever there is a road, you have to follow the road. Right? You can't go where there is no road. Right? So there are two distances what we talk about. One is called the Manhattan distance. Okay, this name obviously comes from Manhattan in New York. Okay, that if you want to go from one place to another place, you have to follow the streets and then get from one place to another place, and because of which your path will not be a straight line path. It will be zigzag like this, depending on wherever there is a road. Okay, so similarly, when we are looking at a grid like it's shown here, I want to go from here to here. Okay, I cannot go straight because I can go only like this. Okay, so this distance is basically called the Manhattan distance. Okay, so in this case, for example, this could be 1 1 1 1. So basically sum of all these all these edges is what we call, sigma of all the edges is what we call the Manhattan distance. The other, of course, you're familiar with is called the Euclidean distance. So if I have a point P here and a point Q there, which has coordinates, so it has P1, P2 and Q1, Q2. So this has point P1, P2 and Q1, Q2. Then the distance, the shortest distance or the straight line distance is given by this. Okay, so this is supposed to be my, this can be X or Y. Okay, so now in this particular case, we see that this is the shortest straight line distance. This is called the Euclidean distance. Now, obviously, you cannot apply that here. Why? Because you cannot actually go straight. Okay, you have to follow wherever there is a road. You have to follow the road. So in path planning also, when we are looking at the path, when you're looking at a path here, for example, all these examples I showed, you want to go from here to here, okay, from the start point to the goal point, and there is a straight line. The straight line is probably like this, but you cannot go on the straight line. Okay, so you have to follow a path which will probably be from here to here, then there, then there. So this is very similar to the Manhattan distance. Wherever there is a road, you can go only there. Okay, so these are two concepts that we use. One is called the Manhattan distance to take you from one point to another point. So when we are saying length, it could basically be the Manhattan path length, or it could be the straight line distance, which is a straight line distance. This is called the Euclidean distance between 2 points. Okay, so when we are saying path length, I have to specify which one I mean, the Manhattan distance or the straight line path. Okay, let's proceed. So the first is uninformed search. Now in uninformed search, for example, you are at the start point here and you want to go to the goal point N. Okay, and you don't have any more information, means you don't know the path lengths, you don't know what is the cost at each state. Okay, in that case, you can simply start searching. Once you search this nodes, then you search this nodes, then you search this nodes, and then finally from there you come and see where is the goal. Okay, so this is basically a way of searching where you have no prior information either regarding path length or about the transition of states. Now something to note about is that when we are talking, the way we are writing this graph is, this is one state. Okay, this is another state. Okay, so it is going from one state to another state, which we call this state transition. So there could be a state transition cost. Okay, for example, the distance to the goal could be a state transition cost, and there could be a path length. For example, the path length could be 2 units. Okay, so this is an uninformed search where you are searching without any prior information, and you want to go from the start to the goal. This is of course not very efficient. Okay, not efficient. And for very large searches, it will become very slow. Okay. Now, the first of the informed search, what we talked about is the informed search, is the Dexter's algorithm. Okay. So Dexter's algorithm goes something like this. Suppose we have a graph like this. This is A, this is C, this is my point. These are the various, I'll just draw the various states. So these are various states. You can consider them to be a network of paths, and we want to go from one state to another. We are here and this is here. Okay, so let us say that this is my state A, this is my state C, this is E. We are just calling them. They can be the vertices or nodes in a graph. This is F. Okay. Okay. So now what we have, what we see here is that these are various nodes of the graph. Okay. Similar to the visibility graph, these can be vertices, nodes, vertices, as in the case of a visibility graph. Now what we are seeing is the path length is there. This is the path length which will take. So if you want to go from A to C, the path length is 1. From C to E it is 4. From C to D it is 3. From B to D it is 3. Here it is 2. Then here it is 5. Here it is 1. And here it is 2. Okay. Now A is my start point. Let's say A is a start point. And my goal point is given here. This is my goal. Okay, so A is start and F is goal. So let us write it down. A is start. Let's write it here. A is start and F is goal. Now I need to find the shortest length path. Find the shortest length path. Okay. Now this is a very simple graph. There are just 3 or 4 branches which are going out, but it can be very complex with a lot of nodes and vertices and edges, right? So you can have a very large number of paths where searching is not very easy. Here you can more or less make out which one is the fastest one. Now in Dexter's algorithm, what it does, it explores nodes ahead with sum of path length. So in Dexter's algorithm, it explores nodes ahead with sum of all paths with sum of path lengths to get there. Okay, so we will start with A and then I will go to C. And so the path length from A to C is 1. Now if I go to E, then the path length to E is, it has come from A to C, C to E, so it will be 5. Okay, I hope you understand that. Now what we do is we start off by making this table, and as I had explained before, we have to write a program which will do this, right? So basically we are making a table. So I start off with A. Okay, this is my A, then there is B, C, D, E and F. Okay, so now what we do is I start point is A, so I'm starting from A. Okay, now from A to B, so there is A and there is B. What is the path length between A and B? It is 2. Okay, so from A I go to B, it is 2. From A, if I go to C, it is 1. The path lengths are already given. Okay. Now you cannot go to D, and you cannot go to E, and you cannot go to F from A straight. Okay. Now out of this, what we see is which one is the smallest, the shortest path length. The shortest path length is C. Okay. So what I do is I box C and I bring it down, and this is C. Okay, so let me write it here. This is 1. So I put this in a box and I bring it down, and this is my C. So the next node that I should try and explore is C, because it has the lowest path length. So I bring C in here. Okay, now from C, now I'm at C. Now from C I want to go to B. Okay, now from C there is no direct path to B, but you can go via A. Okay, so basically what I'm saying is this, please note this, that now this 2 will come down here as 2. There is no direct path, but there is a path via B. Okay, so this 2 comes down here as 2. Now from C to B, C to C is 1, and C to D. Now if you want to go from C to D, so C is here and D is here, what is the total cost? It is the cost of the previous node, how much from A to C, then C to D. So it is 1 plus 3, or 3 plus 1, oh, sorry, it is 1 plus 3. So from A to C it is 1, and then from C to D it is 1 plus 3, which is equal to 4. Okay. Now what about C to E? I'm going from C to E. C to E, A to C is 1, and then from C to E is 4, so that's 5. That's the path length. Okay. Now from C you cannot go to F, so you cannot go there. Okay. Now in this row, which one is the smallest path length? Okay, the smallest path length is 2. Okay, so the smallest path, sorry, I should not have done. Yeah, so the smallest path length is 2. Okay, this is 4, this is 5, this is 1, and this is 2. So what I do is I box it. Okay, and then I bring it down. That means the next node that I'm going to explore is going to be B. So this is my next node that it comes here, and 2 comes down here. So I box it and I bring it down. Okay. Okay. Now I can cross over C, so I don't need to go to C anymore. So C is done already. Now I'm at B. So you can visualize you're at B. Now from B you're going to D. So if you're going from B to D, so from A to B was 2, and B to D is 3, which is equal to 5. Okay, and what about E now? Now B to E. Now you cannot go directly from B to E, but you can go via the previous column. Previous column is saying that the path to E is 5, so I bring 5 down. Please note this. Now what about from B to F? From B to F, you can go from B to F. You have already traveled. A to B is 2 and B to F is 5, so that's 7. Okay. Now in this row, which one is the lowest? So in this row we find that so a point I missed out. Just note here that this is the previous one was 4. Okay, so that means there is a path B to D which is less than 5, so I bring 4 down here. Okay, so I'm going to bring the 4 down here, so please note this carefully. Okay, so in this particular case, although this is 5, okay, B to D is showing 5, but on top there is a 4. That means there is a path which has a lesser cost, and so I bring the 4 down and box it. So I bring the 4 box down here. Okay, so in this row 4 is the smallest, so I make a box on 4 and I bring him down. Okay, now so which was this? This was D. So this is D. The row is D. Okay. Now from now from D, I do not need to go to B. Okay, that's I did not know. I do not need to go backwards to B, so I can cut it out. Now what about D to D? Now D to D, there is a 4 there. It is already 4 here. Okay. Now what about D to E? D to E is 5 because there is a, so D to E there is 5. You can go via 5. So what I do is I bring 5 down. Okay. And what about D to F? So D to F is you have got 4. To come to D, I've gone 4. A to C, C to D, that's 4. Plus D to F is 1. So this is 5. Okay. So in this row, you see that there are 2 low numbers. One is 5. The other is this one is also 5. So you can choose either of the 5s. So let me choose this one. This 5. I box it and I bring it down. Okay. Now, and which column is it corresponding to? It corresponds to E. So from E, so this one is E. Okay, so let me just rub this out. This one is E. Okay, so it corresponds to E, so this one is E. So from E now, I need to go to F. So you can see that from E to F, so come to E, it is 5. 5 plus 2 is equal to 7. Okay, but 5 was already small, so I bring this, I box it and I bring it down. Okay, so compared to 7, 5 is less. That means there is a path which goes to F which has lesser cost. That's the meaning. Now I need to find which is the path. Okay, so how do I do that? So what I do is now, that means 5 is the minimum path length. So what I do here is I follow the 5s up. So from here, so now what we do is we see that there is a 5 here. Okay, now what I do is I take the what is the lowest here? The lowest is F now. Okay, that is my F. So I put F here. The last one is going to be F. Okay, E and F. And in F to F, we just bring this down here. Okay, that is F now. Okay, so it is A, C, B, D, E, F. That is the way we have come. Okay, now what we can do is we look at this column 5 and go up. So I can go up like this. Okay, so from 5 I go up like this. These are all 5s. Okay, now the next one is 7. Okay, so I go up 5, 5, 5. Then I come left to 5, 5, 4. Okay, that means from F I'm coming to left, 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 left. I'm coming till 4. This is the lower one. Then I go up here again. Okay, so I go up here, it comes to 4, and then I can go left, it comes to 1, and then I go up, it comes to 1 again. Okay, so basically I'm following the lesser number path. So from 5 I go up, so these are all 5, 5, 5s. Then I go left. Okay, so from 5 again 5, it comes to 4. Now 4 I go up. Okay, it comes to till 4, and then I go left, it comes to 1, and then 1 I go on top. Okay, it comes to A. Now what will be the path? So wherever there is a horizontal line, Okay, that is going to be, so it is going to be F is the first one, so F. Then the next is the horizontal line, which is D. So let me write down F is the last one. Okay, F just before to that is D, which is D here. Okay, and from D basically I take the next one, which is the horizontal line, which is C, is this one, so I take C. Okay. And then it is A, so it is A. So A, C, D, F. So A, C, D and F is the path that will give me the shortest path. A, C, so A, C, D and F, that is the shortest path. And what is the length of the path? The length of the path is 5. Okay, so basically what we are seeing here is that in using this algorithm, basically we can find what is the shortest path to take you from one node, the start node, to the goal node. Now this, if you can imagine, is that it is exploring all the nodes. Okay, and if there are many nodes and if there are many paths, then this is going to become slow. Now suppose it could be a little bit more informed search. For example, if we knew which is the direction of the goal, then I could search in that direction instead of going in all other directions. Okay, that will make it faster, isn't it? So first of all, what I could say is, if I'm at node D, suppose I'm at node D, okay, and I know I have to go to goal F, then I can have first of all this distance, and I can have a heuristic which will tell me maybe the heuristic can be the distance, and the distance from D to F. If I have that idea, then I can add this and that, and I know I have which side is the goal, and my search is going to become faster. Okay. And that is exactly what is done in the A star algorithm. This is showing the D star, sorry, not D star, it is Dexter's algorithm. So every node is searching the adjoining nodes and is going towards the goal. Okay, just the way we have done. But there are a large number of nodes here. So what is happening is that it is going, the search is taking quite some time, because it is searching on all the nodes. And then finally it will find what is the shortest path. Okay, so you can see that it is taking some time to go from a start, which is here, to the goal, which is there. So it is exploring all the nodes, adjoining nodes, and then it is going to the goal, and then it is finding a path. Okay, so this is Dexter's algorithm, and Dexter's algorithm is a little slow because it doesn't really have any information or idea where the goal is. Okay, so it searches all adjoining nodes and then goes towards the goal and then tries to find out where the goal is. This is exactly how we wrote our table. Okay. Now, if you can think of a faster way to search, is suppose I gave it some information about the distance to the goal. Then it could try and go in particular distance, which will be closest to the goal. Okay, and that is basically my A star search. Okay, so this is Dexter's. Next is A star. So A star was invented by researchers working on Shaky, the robotics path planning, earliest robotics path planning algorithms. So Shaky was the mobile robot which was made in Stanford. Okay, and the algorithm that was used was A star. Now what A star does is it evaluates a function fn, which is a sum of two functions, gn plus hn. Okay. Now this can be the path length till that particular node. Okay. So for every next node, suppose you are at node A and your next node is node B, then this is the path length till this node, till node, and this is a heuristic, which can be the distance to goal. Okay, so basically in the first case, in Dexter's algorithm, we were just looking at the path lengths. Okay, we didn't have any heuristic which was telling me how far is the node from the goal. Whereas here I have a heuristic, and the heuristic can be the distance to the goal. The distance to the goal could be the heuristic distance. So this is my heuristic distance. Okay, so this is the actual distance, which is the Manhattan distance, and the heuristic distance is this distance. Okay, so from this node to this node, this is my distance. So if I talk about this node to this node, the distance could be more. Okay, so basically in the informed search A star, we evaluate the operational cost, which is the path length, which is here, path length, and a heuristic function which is hn. Now information used to find the promising node to traverse, and because hn is there, it is in a way saying that which node has the least distance to the goal, okay, and it should go in that direction. Okay, so let's look at how this is done. Let's take an example, a very simple example again for A star algorithm. So this is my A star. So let's take a graph like this, where this is my start node, okay, S, this is node A, okay, node B, then a node C is here, node C, node D, and then we have node G. Let's say my graph is like this. This goes this way, B to A to B, B to D, D to G, and C can go to D as well as to G, and here A goes to C and S can go to G. Okay, this is an interesting graph. So S is the start node and G is the goal node. This is goal, GOL, goal, and this is start. Okay. Now the path lengths are 1, 2, 5, okay, then 1, 3, 4, 2, and 12. Now this is one set. These are the path lengths. So here we have the GN, which has to do with the path lengths, as in the previous case. Okay. But we also have a heuristic function. Sorry, we have a heuristic cost. Okay. Now this heuristic cost is HN. Now this could be the heuristic cost, could be the distance to goal from that particular node. Okay. So let us say I put my nodes for every node. Let's say for node S, A, B, C, D, and G, each of these nodes, there is a cost associated. Now this cost associated could be the distance. Okay, let us assume it is the distance 5, 3, 4, okay, 260, 260. Okay, so in this case it is made up of GN plus HN. Now let us start off from the start point S. S is my start. Okay. Now from S you can go to A, and you can go to G. Okay. So you can follow this path or you can follow that path. Now if you simply look at this graph, it would appear that why not take the straight road, this one, S to G. You have a cost of 12. Okay, path length is 12. Okay, why not take that one? Okay, so let us see whether that is correct or not. So from S I go to A, and at A basically what we are doing is we are evaluating the function Fn is equal to Gn plus Hn. So this is Gn plus Hn. Okay, and so from S to A, what is the length of the path? It is 1. Okay, plus what is the cost associated with A? The cost associated with state A is 3. So this is 4. Okay. Now S to G, what is Fn? It is Gn plus Hn, okay, which is equal to, what is the path length? It is 12. Okay, so path length is 12, and what is the cost? The Hn, the heuristic, that is 0. So this is 12. Now out of these two, which one is smaller? 4 is smaller. So I box it, as in the previous case. I make a box and I keep this on hold. Okay, that means the next node that I have to search is A, not G. Why? Because the cost of A is less. Okay. Now from then my second step is S to A. Okay, and S to A. From A you can go to B, or you can go to C. Okay, you can see that from S you have gone to A. Now from A you can go to B, or you can go to C. Now if you go to B, then this function Fn is equal to your so it is B. So your A to B is equal to 3 plus 4. Okay, 3 plus 4, which is equal to 7. Okay. Now how did I get 3? So to come to B, So from S to A it is 1, then from A to B it is 2, right? That is the path length. So Fn is equal to 3 to come to from S to A to B it is 3 plus 4. 4 is the transition state transition heuristic cost, which is here, which is 4. So total I get is 7. Now what about from S to A to C? Now if you look A to C, Fn will be equal to get to C you have come from S to A, which is 1, and then A to C it is 1, so it is 2 plus, and the heuristic cost for C is 2, so it is 4. Now out of 7 and 4, basically this one is smaller, so I box it, okay, and I keep this on hold, okay. Now which basically means that I'm going from S to A to C. Now from C you can go to D, and so I have gone from S to A, from A I have gone to C, and from C I can go to D, and I can go to D, or I can go to G, okay. So when I'm going to D, the function Fn is equal to D. Where is D? D is here. So from C to D I have gone from S to A, which is 1, then A to C, which is another 1, and then C to D, which is 3, so it is 5, plus the heuristic cost is 6, so it is equal to 11. Now what about C to G? C to G is C to G has a cost of 4, the path length, so Fn is equal to, how much is this equal to? C to G is equal to, C to G is equal to 6, is equal to 6, plus G is 0, so it is 6, okay. Now out of these two, which is smaller? 6 is smaller, so I box it. Now if you see, you have reached G, and which was the smallest, which was the shortest path? It was S to A to C, C to G, okay. I hope you can visualize that. So this is giving me 6, and that is the shortest path length, okay. So what you can see here is that this one is giving us the shortest path length, so S to A to C, and C to G. That is the shortest path length. So although by looking at this graph, it was interesting, I said, because by looking at this graph it appears that this path length would be the shortest, okay, because it's a straight path, but it's not. So this one is smaller, it's shorter, okay. So this is basically A star. Now in A star algorithm, what we saw is that we have a Gn, which is the path length, and we have an Hn, which is the heuristic cost, okay. The heuristic cost can be anything. It can be energy, okay, it can be distance to goal, okay. Now it can be anything else, okay. So in this particular case, this is faster than your Dexter's algorithm. Now suppose you can imagine that we have already assigned weights and the straight transition like this, but when the robot is traversing, suppose there is an obstacle now, okay, then what it can do is, suppose there is an obstacle, so what the algorithm can do, it can raise or lower some of the transition costs, okay. Say for example, if it is going towards D, and here it finds that there is an obstacle, okay, so what it can do, it can raise this one's cost and make it maybe 20, so the robot doesn't go in that direction again, okay. Or if it finds that it is free path in some direction, it can lower the cost. So you can dynamically change, so dynamically tune or change this Hn, okay, the values of the heuristic Hn, and this is what we call the dynamic A star, or which is called D star. So we looked at blind search, then we looked at Dexter's algorithm, we looked at A star. Now D star or dynamic A star is exactly same as A star, the only difference being that you can change this, you can raise or lower those weights as you go along, okay. So the robot doesn't get stuck somewhere, okay, or if there's an obstacle, the robot understands that there's an obstacle there now. So here you can look at an example that where there is a start point and there is a goal. Now the robot is starting off by going straight towards the goal, because that is the direction in which the distance is least, okay. And as it is hitting that obstacle, what it is doing, it is finding surrounding areas, okay, and then it is going again towards the goal and it finds the path. That's it, that's the path. Now you can see it's interesting that it did not search here, it did not search here, like unlike the Dexter's algorithm where it was searching everywhere, Okay, so here you can see it. Let me it starts off simply by going in the direction of the goal. Why? Because it knows the heuristics that hn is in that direction. Okay, and gn plus hn. So hn is a straight line direction towards the goal. So that is why it is going towards the goal first. Then it hits the obstacle and then finds the bypass and then goes off this way. Okay. So it did not search anywhere there, did not search anywhere there. So this is much faster. This is another example of A star algorithm. Okay. So these are various nodes. Now in the previous case, the example I just solved, there are very few nodes. There are 1, 2, 3, 4, 5, only 6. But you can imagine that in a real world situation where there are many obstacles, there are many, the robot is going, there are many obstacles. Okay, this is a very large workspace. The network of paths can be very, very large. Or if you're looking at a grid search, then the number of grids could be very, very large. Okay, so in such a case, what we can search this way. So this is A star, and this is exactly how it operates. So we start off from A, which is my start, and this is my goal point. Okay, so I start from A, and this is the list from A0. I'm starting from A0. I'm searching this nodes E, B, and H. Okay, so from here, I'm going here, here, and here, and I'm writing it this way. Okay, so I'm maintaining this list, and then from the list, I'm expanding. Okay, exactly the same way that I did before. Now, out of this, you can see that which one has the least cost? It's E, B, and H. It is E. So the next one that I'm going to do is going to be E. Okay, so the next one I'm going to search. So E comes here. E comes there. Now again, the way I'm getting the value of E is essentially 3. So you can see E. How did I get E? It is 3 is the GN plus HN. Where is E? E is 8. So HN is 8. Okay, that's how I got 11, which is equal to 11. So exactly the same way that I had done it in the previous example. So we get E, so E will come here now. Okay, so E has come here. Now E is connected to what? E is connected to F, I. So E is connected to F and I, and B and H are there from before. Okay, so I'm adding I and H to this queue now. Now out of this, the cost is least for I. So next I will come there. Okay, so this is how I'm expanding. So I comes here. Now I is connected to J and M, L and F. So L and M and J and M, and this side is connected to L and F. Okay. Now here, which is the least? These two are least, so you can take any one. Okay. So I took J. Now where is J connected to? J is connected to K, G, M, and N. Okay. So J is connected to M, N. So I'm taking M, N, G, and K, G and H. Sorry, G and K. Okay. These are the associated costs. Again, you find which is the least cost. Okay. Out of here, which is the least cost? So it is M. So M will come there now. Okay, so M has come there. Now M is connected to what? M is connected to L this side, is connected to N this side. So M is connected to N, and it's connected to L. So what is the cost? Okay, so we find the cost again. Now what we do find is that although it went this side, this connection doesn't give you the least cost. Okay, so I connect it this way, and what we find is that is because the optimal path is not this one, but is this one. Okay, this is my optimal path. Sorry. So the optimal path is this one now. Okay, so my optimal path is this one. Now it's exactly the same way that I had done in the previous example, but this is using you can say pointers, in which we are keeping nodes, or we are entering nodes and throwing out nodes depending on which one is the least cost. Okay. Now the next thing that we need to look at is D star, and then we will look at, now in D star, as I mentioned, that D star basically stands for dynamic A star. Okay. Now in dynamic A star, our cost parameters can change during the problem solving process. So replanning can be done online. Say for example, there is some place where there's an obstacle. Okay, so you can replan that area very quickly. Or dynamic, in case where the system is moving, there is a dynamic obstacle now. In case of dynamic obstacle, you have to dynamically change the weights. That is basically where we use D star. There is also something called D star light. Okay, so d star light is also there. Now the benefits of the d star is that basically it's optimal, complete. It is more efficient than a star because replanning is expensive in complex environments where the environment is very complex. Now the local changes in the world do not impact on the path much. So most costs to goal remain the same, and it avoids high computational cost of backtracking. Okay, so basically this is the basic differences between Dexter's algorithm and D star. Okay, and this is A star. So these are the comparisons between Dexter's algorithm, A star, and D star. Okay, now what we'll look at next is trajectory planning. Trajectory planning for a serial arm. Now, what this actually means is that when I have a two-link manipulator, for example, like this, I want to go from this point P1 to the point P2. I want to go like this, and I want to go here, P2. That's my point P2. Okay. The actual planning will not be done in the Cartesian space. It is done in the joint space. Okay. So I want to go from here to here. I may be able to go via this point also. I can call it P3. Okay. But the controller basically will control the joints, right? Theta 1 and theta 2. That is what you're controlling. So the controller will actually move the joint, and then it is going to take the end effector from point P1 to P2. Okay. So a path is basically a continuous function. Okay. So a path is a continuous function, and there is no time here. Whenever we talked about, in all the earlier examples I talked about, there was no time. Time was not there at all. But to go in the real world from one point to another point, you have to control the joints, the joint angles. Now, this is basically what we call a trajectory. So, a trajectory is the history, time history of theta dot and theta double dot. Okay. So here there are two thetas, theta 1 and theta 2. So I need to control theta 1 and I need to control theta 1 and theta 2 separately. Okay. By fitting trajectories to theta 1 and also fitting trajectories to theta 2. Okay. So in this case what we do is, let me draw an example here. So this is my, let's say theta naught. It has to go from theta naught to theta f in time tf, this time 0. Okay, time tf. So basically what we have to see is the trajectory has to be fitted, which will take the joint from theta naught to theta f in time tf. So theta naught to theta f in time tf at joint. Now because of this joint motion, there will be an end effector change, end effector position change. Okay. So here I have to fit a trajectory which will take it from theta naught to theta f in time tf. Okay. So path is not enough. We have to come to motion planning. So in motion plan, I have to worry about the trajectory of motion. So how do I fit, what is the equation of the trajectory that will take me from theta naught to theta f? So in two-link manipulator case, there will be two trajectories. This is independent joint control, right? So here we can say that we are fitting a trajectory which is going to be theta naught is equal to a naught plus a1t plus a2t squared plus a3t cubed. So this is a cubic polynomial. Now I cannot fit an equation less than order 3. Why? Because if I only put a naught and a1t, then what will happen is if I take theta dot t, then what will happen is theta dot t of this equation is equal to, so I take the derivative of this to get, so this is position, right? What is velocity? I take the derivative of that, which is a1 plus 2a2t plus thrice a3t squared. Okay. I differentiate it again. This is my velocity. Now if I differentiate it again, what will I get? Theta dot double dot t, which is acceleration, is equal to 2a2 plus 6a3t. This is my acceleration. Okay. So now I have got my position, velocity and acceleration equation. Now suppose I had used only theta t equal to a naught plus a1t. What would happen is, if I differentiate it, it will become a1, which is a constant. Okay, so this is constant velocity, and theta double dot t will become equal to 0. So acceleration is 0. So you cannot represent motion, the trajectory, by using this equation. Okay. Similarly, if I took only plus a2t squared, then what will happen is your velocity will become plus twice a2t and your acceleration will become equal to 2a2. This is a constant. Okay. Now this is also not possible. Why? Because you know that when the joint is moving, it will have to accelerate, remain constant, and then it will have to decelerate again like that. Okay. So neither can velocity be constant nor can acceleration be constant, and obviously acceleration and neither of them can be zero. Okay. So it will vary as we move along. So what I'm trying to explain is that you have to take minimum cubic polynomial. If you take less than cubic polynomial, your velocity and acceleration will have problems. Okay, and you will not be able to move, the robot link will not move. So now, we have taken our three equations, that is theta t is equal to a naught plus a1t plus a2 t squared plus a3 t cubed. Okay, and theta dot t, the velocity is equal to a1 plus twice a2t plus thrice a3t squared, and theta double dot t is equal to twice a2 plus 6 a3t. Now this has four constants, right? A naught, a1, a2, and a3. So I need four conditions in order to be able to solve them. So when we looked at this manipulator, let's take the example of a single link manipulator. It is moving from, let's say, from this point, this position to this position in time tf. So theta naught, that's theta f. Okay. So at start position, at theta is 0, it is at theta naught. When it has reached the final position, theta tf, the position is theta f. Okay, so I have two constraints. Now what about velocity? Here it is at stop, it is at rest. Okay, so before starting, this is at rest, and here also it stops motion. Okay, so it is at rest again. So it is at rest means at time equal to 0, the body was at rest, velocity was 0, and velocity at tf is also equal to 0. So I have four equations now. Okay, so four equations, four unknowns here. So what I can do is I can put this one of this at a time in these equations, and I can solve. So when I put this in, so I put them in these equations. So for example, if I take theta is equal to 0 is equal to theta naught, so what would happen is theta naught, time is equal to 0, t is all 0, is equal to a naught. That's from the equation 1. So from here I get the first one, right? So a naught is equal to theta 1, I get the first constant. Then if I put the second one here into the velocity equation, what will I get? At time is equal to 0, velocity is equal to 0. So time is equal to 0 means t is equal to 0. So velocity is equal to 0 means a1 is equal to 0. So this constant a1 will become equal to 0. Okay, so I've got two of them straight. Then I have two more equations. I can put this one and this one, okay, in the position equation and in the velocity equation, and I can solve. a2 is equal to 3 times tf squared divided by theta f minus theta naught, and a3 is equal to minus 2 times tf cubed theta f minus theta naught. So I've solved for the four constants. I've solved for the four constants, right? a1, a2, a3, and a4. So now what we can do is we can write our equation in terms of this, right? So what we can do is I know the values of this, and this, provided I know what is the start point, end point, what is the start velocity, end velocity. Okay, so having known this, I have solved for this equation, right? For this equation, I have solved the constant values. So let's look at a very simple example. A link moves from 20 degrees to 68 degrees in 4 seconds. Let's say we have a single link. It's moving from 20 degrees to 68 degrees, okay, in 4 seconds. Okay, so there's a single link which is moving from 20 degrees to 68 degrees in 4 seconds. Okay, calculate the position, velocity, and acceleration. Find theta, theta dot, theta double dot with respect to time, so that the link is at rest at start and end. That means velocity at start, velocity at end is 0. So I can write down the equation of the polynomial. Theta t is equal to a0 plus a1t plus a2t squared plus a3t cubed. Okay, and by using the previous values that we found, whatever we found here and here, I just put in the values. Okay, so theta naught, so this is my theta naught, that's my theta f, time tf is there. So I can find out very easily putting these values. I get theta naught is equal to 20. This gives me a naught is equal to 20. Theta naught 0 is equal to 0 gives me a1 is equal to 0. And theta at tf is equal to 68 degrees. This gives one equation, 16a2 plus 64a3 is equal to 48. Theta naught tf is equal to 0 gives the other equation, 8 plus 48a3 is equal to 0. Now I have two equations, two unknowns. I can solve them very easily and find a naught is equal to 20, a1 is equal to 0, a2 is equal to 9, and a3 is equal to minus 1.5. So if I put this equation into the equation, what we do get is theta of t is equal to 20, the cubic polynomial, plus 9t squared minus 1.5 minus 1.5 t cubed. And theta dot t is equal to 18t minus 4.5 t cubed. And we have theta double dot t is equal to 18 minus 90. So what we can do now is that, so I can plot basically, so it is 4 seconds, okay, time tf is equal to 4 seconds, and this has moved from, 20 degrees, so I say 20 is here and 68 is there in 4 seconds, okay. So now I can plot. Now how do I plot? So I divide this into, say, time instance of 0.1 seconds each. I take that 0.1 second in time, so 0.1 second intervals of time, put that t in here and find what is position, velocity, acceleration. So what we do get is position varies something like this, that's my position theta. Your velocity will be varying something like this, so this is a halfway mark. So in the halfway mark it will be maximum, like this, and like that. So halfway, this is not halfway. So exactly halfway mark. So let's say this is my halfway mark. Okay, that's 2. So this is my theta naught, and my acceleration is going to vary like this. It will come down like this, That's my theta double dot. How did I get these values? I simply took different instants of time, put them in this equation for position, velocity, acceleration. Whatever values I got, I plotted them here. So what you see that we have got the trajectory of the joints, and this trajectory of the joints is the one that will be used by the controller, which is going to move the joint from here to here. So in the case of a multi-degree of freedom manipulator, like the example I showed some time back here, okay, each joint will have one cubic polynomial. Okay, so this will have another cubic polynomial. They will fit the trajectories onto that cubic polynomial and then operate in real time. Then they'll operate to take the end effector from the start point to that point. Now suppose you want to go via this point, then you can go from here to here and then here to here. So whatever trajectory we have found, for example, in the case of obstacle avoidance, this is an obstacle. Okay, I want to go from here to here and my path is something like this. So I can put a via point here and say the path will, the first trajectory will take from here to here. That's my trajectory 1. Then the second trajectory will take it from here to here. Okay, and this is how the planning is done at the trajectory level, or the motion planning is done. Okay, so today we looked at the basic search algorithms, that how do we search given a network of paths. So after we find the best path, then we have to go on the path. In the case of a mobile robot, it is the robot has to be actuated to go on the path. In the case of manipulator, given the end effector path, you may have to find the joint trajectories as by fitting a cubic polynomial. So we'll stop here and then continue in the next class. In the next lecture, we'll be looking at motion planning with kinematic constraints, and then we'll move on to grasping and applications. Thank you.